So, all right, here we go. Lots to do today. So let's get started. We'll just pick up right where we left off. Which is, remember we were talking about necklaces. Okay, so we're ready for number 32. There is a lot to keep track of, so let's make sure we're keeping our thoughts organized. Here we go, and we'll review a few of the things we talked about the other day too. But here we go, we got 2 blue, 3 yellow, I'm on number 32, 1 green, 4 orange, 1 pink, 1 purple, and the beads of each color are alike. Now, what does that mean? That means that all of the blue beads look exactly the same. So think about that for a second. Remember when we looked at the word Mississippi? Remember what we had to do with that? We had to divide out the duplicates. So since in Mississippi there were 4 S's, remember dividing by 4 factorial? That's what we do when we have identical things. All the S's in the word look alike. They're identical. Well, these blue beads are identical. So we're going to be dividing by the duplicates, just like we did letters. First question says, okay, we're going to make a necklace. And it doesn't have a clasp. So in other words, it's an unbroken circle. So what's the rule for circular arrangements? You subtract 1. So how many beads do I have all together? Count them up. I don't care what color they are. I don't care anything. Count them up. How many beads are there? All right, there's 12. So since there are 12 beads, I am going to start with 11 factorial. Because a circular arrangement is 1 less. Okay? Now, I'm going to divide by anything that's the same. So I'm going to divide by 2 factorial for my blues, 3 factorial for my yellows, and 4 factorial for my oranges. Is that okay? And then I'm going to remember that there is a little kind of peculiar consideration I have to have if my circular arrangement is handheld. If it's handheld, which a necklace is, honestly, necklace, bracelets, keychains, that's it. We have to do reflections, and we handle reflections by dividing by 2. Because if I were to draw an arrangement on the blackboard, I would also draw another arrangement, but in reality they're not different. They're just looking at the same thing from both sides, right? So I'm going to have to divide by 2. All right, let's type that in our calculators and see what we come up with. Remembering that we either put this in parentheses or we divide by each of these individually. So 11 factorial divided by 2 factorial divided by 3 factorial divided by 4 factorial divided by 2. Either way is fine. And either way is kind of a pain in the butt, but it is what it is. And I need you to be typing it in. I typed it in. I need you to type it in and tell me if you get my answer. You did. Perfect. you didn't, it's problematic because that's what goes in the answer blank. So get it, practice it. Now, what changes on the problem? One thing changes on the problem if we put a clasp on the necklace. It's still a necklace, so I'm still gonna have reflections. I still have duplicate beads, but now I have a clasp, which you can think of as an extra bead, or you can think of it as creating a line now when you unclasp it. So what's the one thing that's gonna change for problem B? That's gonna be 12 factorial. That's gonna be 12 factorial. That's the only thing that's different. So that question, I got 831,600, 831,600, is that what you got?
Yeah.
Perfect. Okay, so that problem had a lot of review in it. We talked about how to handle circles, talked about how to handle duplicates, and how to handle necklaces, bracelets, and keychains, what are called handheld circular permutations. Okay, now the next problem is a new concept. Here's the deal. We got 6 couples going to the movie. Alright, sit in a row together. Now, if anybody could sit anywhere, 6 couples would be 12 people. And how many ways can 12 people sit in a row? 12 factorial. Easy. But this is like a date. So they want to sit by their date. Okay? So if Peter and I go to the movie, we want to sit together. Right?
Yeah.
Okay. So how does that change things? Huh?
Has to be like sitting around.
Yeah, so these 2 have to be together, and those 2 have to be together, and those 2 have to be together, and so on. Yeah.
Would it just be 6 factorial?
Oh, what a great start. Not the end, Van, but a great start. Van says, would it just be 6 factorial? And the answer is yes, because if Peter and I have to sit together, it's like having a string tied around us. We can't be separated. And there's a string around you guys and a string around you guys. So really I'm not arranging 12, I'm only arranging 6. We call it bundling. We've got 6 bundles. But the reason it's not over is because when you tied Peter and I together, you could have tied us together like this, or you could have tied us together like this. In other words, our bundle, Peter and me, our bundle could be arranged 2 factorial ways. There's 2 of us, and we could be lined up 2 factorial ways, and they could be lined up 2 factorial ways, and they could be lined up 2 factorial ways. So each couple can be rearranged. And there's the answer to the question. So when we say things are bundled, we start with the bundles factorial. There's 6 bundles of people. But then you must multiply by each bundle factorial. Now, Meg, I know that 2 factorial is 2, but I want you to think about this as 2 factorial, because if there were 3 people in the bundle, it wouldn't be 3, it'd be 6, 3 factorial. So we take each bundle factorial. Okay, so what's the answer to that one? Hang on for a minute here. Did you get 46,080? All right, number 34. How many ways can you, that should be arranged, 7 identical algebra books. Okay, so I have 7 algebra, and they're all the same. I have 4 geometries, and they are not the same. They're unique. They're different. And I have 3 trig, and they are the same. And I'm going to walk in. Question number A says, put them in a row. Here's all the books. Put them in a row on the shelf. What do I start with? Add them all together. How many books do I have?
14.
I have 14 books. 14 books can be arranged 14 factorial ways in a row. Now, if I were at the library and they had one of those spinning, you know how they have those spinning bookshelves, those circular bookshelves, then it would be 13 factorial. I'm putting them in a row. Am I done? Is this it?
No, there's like.
What do I have to do?
Divide by.
Divide by anything that's a duplicate. So I'm going to divide by 7 factorial and divide by 3 factorial. Just like dividing by 4 S's and 2 P's, or whatever it was in the word we did the other day. So, what do we come up with? I got 2,882,880. How's that sound? Did I do that right?
Yeah.
That's what you got? Okay. Everybody keeping up here? Let's look at the next one. We're going to put them in a row again. But the books of each kind are kept together. So this is like the couple problem. When I go to arrange my books on the shelf, I want all the algebra together, and the geometry together, and the trigonometry together. Okay, so where am I starting, Katie?
Is it 3 factorial and then times 7 factorial times 4 factorial?
Beautiful. Because, remember, when I bundle things, which now I'm bundling books, I gotta keep the books of each kind together. So I put a string around these, and a string around these, and a string around these. These are strung together, they're bundled. So I really only am arranging 3 things. There's the bundles. But when I tied a string around each of these, like look at these 4 books. Can't those 4 within that bundle be arranged 4 factorial ways? And so on. She's left out one thing though. What do I still need to do? Divide. So I still need to divide by 7 factorial and 3 factorial. And what will happen is we got some canceling going on, that's fine. So your answer is just whatever 3 factorial times 4 factorial is. Nicely done. Kamara, what'd you get? 144, she says, 144. Now, one more. All these same books, but now only the algebra has to be kept together. Okay? I want you to think about this. For whatever reason, I said, okay, I'm going to have all my algebra books together. I don't care where any of the rest of them are. So this is a bundle that's functioning as one, because there's a string around it. These guys are not bundled. They're free. So how many things am I arranging?
7?
8. I'm arranging 8. Why am I arranging 8? Because I got 3 of these, and 4 of these, and 1 of these. A bundle of these. So I'm starting with 8 factorial. 3 and 4 and are tied together. But they're a bundle, so I have to multiply by 7 factorial. But I'm going to turn right around and divide by that 7 factorial. So that will be my answer. Mara is my resident calculator expert, so I'm waiting on her. 6,720. All right, now, just to make sure that this is gelling with you, go back to our books. Suppose that I had, again, well, who knows why, I want to keep the algebra books together and the geometry books together. I don't care about these guys, they can be anywhere, sprinkled in among these things, but these have to be kept together. All right, so what am I really arranging? 5, 3, 4, 5, right? Okay, bundles count as 1. Free things count as however many there are. Okay? Whew, that's a lot. All right, let's do some problems by hand. Honestly, I can't remember. Did we talk about doing these problems by hand yet? Nope. All right, so we're starting from scratch. So you know, if you type this in on your calculator, I mean, he just does it. What is happening in the background? Well, the formula for permutations, and what's the difference between P's and C's? Permutations, combinations, what's the difference?
Combinations not.
One order matters and one it doesn't. So permutations, order matters. Combinations, order doesn't. I'm ready to submit. Throw out an example. Suppose in this class, 25 of you, and I'm going to give away 3 identical blue markers. Okay, so 25 kids, I'm going to pick 3 and give away 3 identical blue markers. Is that 25 P3 or 25 C3? C. Because if you're getting a blue marker and you're getting a blue marker and you're getting a blue marker, do you care if you're picked first, second, or third? No, you're getting the same prize. But if I come into the room and say, okay, I'm gonna give away a $100 bill, a $10 bill, and a nickel, then it's 25 P3, because then you care if you're picked first, right? See the difference? Okay, well, back to the formulas. The formula for NPR, this is what the button looks like on your calculator. The formula is n factorial over n minus r factorial. So in other words, you take this number, factorial, and divide it by the subtraction factorial. So if I am doing this by hand, no calculator, I'm going to have 10 factorial over 7 factorial. And again, I'm not panicking about this at all, because what does 10 factorial mean? 10, 9, 8, 7, da-da-da-da-da-da, divided by 7 factorial. What's going to happen? All that's going to cancel. So the answer is 720. Easy. Now, they don't always work out that simply, but that one sure did.
We can still just do 10 factorial divided by 7 factorial, right? Like on our calculators.
But it says by hand, it says evaluate by hand.
Okay.
Yeah. No, if I'm using a calculator, I'm not even doing that. If I'm using a calculator, I'm just typing that
You
in.
can type it.
But when I'm doing it by hand, then I don't have a calculator. So this is the strategy I'm going to use. Now, if it's a combination, the formula is very similar. it starts exactly the same, but there is an additional r factorial down there. So with a combination, you have this number on top, then you subtract, but then you also have that number on the bottom. So 10C3 would be 10 factorial over 7 factorial, 3 factorial. So that means, by hand, 10, 9, 8, and then everything else is gonna cancel with that. With me? But I still have this now on the bottom, so I still have a 3, 2, 1 on the bottom. So 3 goes into 9, 2 goes into there. It looks like the answer is 120.
So do we have to do like canceling?
Do we what?
Do we have to do like canceling? Like when you cancel the 7, you put like a 10 on 8.
Yeah, well, I mean, 10 factorial is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 7 factorial is 7, 6, 5, 4, 3, 2, 1. So all that's gonna cancel. I just did it without writing it all out.
Yeah.
But if you wanna write it all out, go ahead, I don't care.
So do we have to do that?
As
Or
opposed to
we can't
what?
use our calculator?
You can't use your calculator. I mean, if you wanna multiply all those numbers and multiply all these and then do the division, that's up to you, but I think this is way faster if you're doing it by hand. Again, this is no calculator. If I have a calculator, I am typing this in. I'm not even messing with it. Okay? All right. Perfect. All right, now we're switching gears. And at first glance, you're not gonna even see any kind of connection at all. But I promise you will see a connection. All right, so here we go. For this first beginning here where it says expand, well, I mean, some of them you know the first one. X plus y to the first is just gonna be x plus y, agreed? Easy. X plus y squared, now remember, that means a FOIL. That's x plus y times x plus y. And you have done that many times, you could probably just do it in your head. If not, you'll actually FOIL it out. But the purpose of this is not to have you do a ton of foiling. So, I'm just gonna tell you, and I want you to write it down, what x plus y cubed is. I'm just gonna tell you, I want you to write this down. X plus y times x plus y times x plus y is x cubed plus 3x squared y plus 3xy squared plus y cubed. Just write that down. I know that if I gave you a few minutes, you could FOIL this out. That's not the point. That's first year algebra. That's not the point of this exercise. This is what you get if you FOIL it out. Maybe one more. X plus y to the 4th. This is what you get if you FOIL it out. Now, as you're writing that down, I want you to be kind of looking at it and seeing if you have any, you see any patterns, if you have any observations at all. Because I'll tell you right now, guys, I am not a genius. I cannot do that in my head. I am 64 years old, half my brain is gone. I haven't memorized this. There's a pattern. There's something going on here. And I would like your help figuring out x plus y to the 5th. can you figure out any part of that? Maybe not the whole thing exactly, maybe the whole thing exactly, but any part of it. So it's gonna start with an x to the fifth, and it's gonna end with a y to the fifth. These are the observations we're having. What other observations? Meg?
Plus 5x 4 y?
I don't know. Is that what you think?
That's
All right, that's what we think, okay. Any other observations? Again, maybe not the whole thing, but do you see any kind of pattern happening?
Second question, 5x, 4.
So this is gonna be 5x, y to the fourth, he says. Now I want you to notice, okay, when we did it to the fourth power, when I wrote this one out, the first term was an x to the fourth, the second term was an x cubed. The next one was, what's happening to the x's? They're going down. So it seems like, I'm not sure about the number, but wouldn't this one be an x cubed, and this one would be an x squared?
Yes.
And then the y's are the same, but other direction. So this is gonna be y squared and y cubed, and there's your y to the fourth. So, big important observation. Two of them actually are here. When you're going to the fifth power, the first x is x to the fifth. And then as you progress down through the terms, the powers on x keep going down, and the powers on y do exactly the same thing, but from the other direction. Right? Looks good. Second observation. Notice that within each term, what do the powers add up to? They add up to whatever your expansion is. So your exponents will add up to, in other words, the degree of each term will be the degree of your expansion. Now, what's the only thing we can't quite figure out? Some coefficients here in the middle. You looked at the pattern and said, okay, this is gonna be a 1, this is gonna be a 5. In the next one, this would be a 1 and this would be a 6. It's the ones in the middle that are a little bit more confusing. So, I'm gonna step over here and I'm going to write down just the coefficients. So, first one was 1, 1. Second one was 1, 2, 1. 1, 3, 3, 1. I'm writing down just the coefficients. This, what?
The 3 and the 3, like the 2, like if you, it's like a pyramid, or like a triangle.
So if we add these two, we get this one. If we add these two, we get this one. So the next row, which is the ones we're trying to figure out, again, I'm gonna erase some of this. We're gonna start and end with a 1. This is gonna be a 5. Then I'm gonna have a 10 and another 10 and a 5. So those coefficients, we had the 1 and the 5 already. I'm gonna put a 10 here, a 10 here. There's my 5 and 1. There it is, done. That's cool. So what would x plus y to the 6th be? Well, let's put all this together that we've observed. First of all, our coefficients are going to be 1, 6, 15, 20, 15, 6, 1. Would you agree with that?
Yeah.
So those are my coefficients. 1, 6, 15, 20, oh shoot, I'm running out of room. 15, 6, 1. Those are my coefficients. Now, what did we observe about the variables? X to the 6th, X to the 5th, X to the 4th, X cubed, X squared, X to the 1st, and technically X to the 0. What's X to the 0? It's 1, yeah, so it's like it's not there. And then your Y's are doing the same thing, so Y to the 6th, Y to the 5th, Y to the 4th, Y to the 3rd, Y to the 2nd, Y, and Y to the 0th. And as Meg said, I don't really have to put in the zeros. Done. Oh my gosh. We just expanded x plus y to the 6th power, foiled it 6 times in about 30 seconds. Cool. All right, Kara, did I lose you? You have some kind of stunned look on your
A
face.
little bit. But,
Where did you get lost?
now it was showing me the pyramid more because I couldn't see it, but I see it now.
You see it now?
Yeah.
This pyramid, as you call it, I have erased part of it, but this is actually called Pascal's triangle. And I'm going to show you now, you're going to discover what it has to do with this chapter. Why are we doing this? It seems unrelated to what we just did. So, Eli, your row, so you guys over there against the wall, I want you to take out your calculator and I want you to type in one thing. I want you to type 5C5. Actually, no. I want you to type 6C6. Okay, Amanda, your row is gonna type in 6C5. Robbie, you guys are doing 6C4. Peter, 6C3. Sydney, 6C2. Kamara, 6C1, and I'll do 6C0. Alright, so we're typing them in. Every row's typing them in, giving me a number. So Eli, what'd you get? 6C6?
Yeah.
1. Yep, Amanda, what'd you get? Uh-huh. Okay, perfect. You guys got it? 15? Peter, what'd your row get? 20? Sydney, what you guys got? 6C2? Uh-oh, she didn't know how to type it in. Kamar, she needs some help. What'd you get?
6.
6C2 was,
Oh no, I'm 62-1.
you're 6C1, you're
Yeah.
6, yeah. So Paige, what'd you get for 6C2? Okay,
It's 15.
Alex, you got 6C2?
15.
You're right. And I did this one and it's 1. Now I want you to look at that. Have you seen those numbers before? Those are the numbers in the 6th row of Pascal's triangle. So, we got those numbers a very different way. We got it through adding, but you can also generate Pascal's triangle by doing the combinations. So if you're expanding, let's say you have a problem, and you have to expand it to the 15th power. Well, I don't really want to write out 15 rows of this triangle. I could. I don't really want to do it. Instead, I can go back and what would the coefficients, what would the numbers be in the 15th row? Well, the first one will be 15C15. And then 15C14, 15C13, and so on, all the way down to 15C0. All right. Now we have to do some variations of this. So, I don't care how you get the numbers, guys. If you have the triangle already drawn, you're welcome to use it. You're also welcome to use the combination numbers to generate your coefficients. Alright, so what changes now with this kind of a problem?
There's a coefficient.
Which, I erased my triangle, but hopefully you have it written down. What are the coefficients that are gonna show up if I'm expanding to the fourth power? 1, 4, 6, 4, 1. What are those numbers, you guys? Those numbers are the fourth row of your triangle. Did you write it down? Look at it. Aren't those the numbers in the fourth row? If you are expanding to the fourth power, those are the numbers you start with. Now, there's another number inside of this problem, and so that's gonna ultimately affect my answer, but not my setup. If I'm going to the fourth power, it's going to be 1, 4, 6, 4, 1, period, to start. Now, in the one I did earlier up here at the top, it was just a plain X and a plain Y, so that was easy. This one is not so easy. It's a plain X, but it's a negative 2Y. So my variables this time are not just X and Y. They are X and negative 2Y. This is one variable, this is the other variable. In the ones I did earlier, this was one variable and this was the other variable. See, those were easy. Now it's gonna be a little more complicated, but the process is exactly the same. This is to the fourth power, so right here on this X, the exponent's gonna be 4. Would you agree with that? And then what are those X's going to do? Count down, and eventually the last one is going to be X to the 0th, which I don't even need to write down because that's just 1, right? Now what about the Y part? They go up from that end or down from this end, depending on where I'm starting. But yeah, they go in order too. And again, I can just erase this one because it's to the 0, so it's not there. These are my terms. Simplify. X to the 4th. Now be careful. I know that looks like a minus. That is not a subtraction. That is a negative sign. This is multiplying. This is all multiplied. So I am multiplying a 4 and a negative 2. So this is going to be minus 8x cubed y. Do you see that? Now what's this one going to be? Again, it's all multiplied. Be careful. What is it? Yep, 24. X squared, y squared. Why is it positive 24? Because negative 2 squared is 4. And 4 times 6 is 24. These powers go with the entire variable, and the variable is negative 2y. Alright, this is multiplying now, all multiply. What's this one going to be?
32.
Negative 32. X, y cubed. And what am I going to have on the end? What's my last one going to be? 16, y to the 4th. Positive 16, y to the 4th. Quit watching that clock. 9, one more of these, and then we'll look at a different, scenario. But let's do one more of these. 2x plus 3y to the third. All right, so what do I start with?
1, 2x.
I start with the foundation, and it's not 1, 2, 1, it's 1, 3, 3, 1. I gotta go to the third row. So 1, 1 is my first row. Then I have the 1, 2, 1 row, and then I have the row I need, which is 1, 3, 3, 1. Now next to each of these, I am going to put a 2x and a 3y. Because in this problem, those are the variables. Agreed? Those are the variables in this problem. Now, exponents. Remember that if you are expanding this, your first variable starts out going to the third and then counts down. The second variable does the same thing. Down from that end or up from this end. And again, your little check is, notice, what do these powers add up to? They have to add up to 3. All right, we're done, except for simplifying. Here we go. Now remember, anything to the 0 is 1, so that's like not there. What's my first term? 8x cubed. Perfect. All multiplication.
36x squared.
3 times 4 times 3. So 36 x squared y. Beautiful. Three times 2 times 9. 54 xy cubed, xy squared. And on the end, again, don't let this confuse you, it's to the 0, not there. So that's gonna be what? 27 y cubed. You're doing great. You're doing absolutely great. All right, now we got this guy. Now, doing exactly what we just did, could we write out this entire expansion? Sure we could. It would take a long time. It would be very, very big, but we can do it. Luckily for us, we don't want all of the terms. We only want the fourth one in the list. So for example, like this is the second term. That's what we want, just one of those. Would you agree that every term, including the one I want, will have some kind of a coefficient, some power of x, and some power of y in this problem? So let's think about it. I don't know what the 10th row of Pascal's triangle is. You know, like this was 1, 3, 3, 1. I got that memorized. Okay. I don't know the 10th row. So it's going to be the first number in the 10th row would be 10C10, 10C9, 10C8, 10C7. So the coefficient that I need is 10C7. You could also build Pascal's triangle and count over to the fourth number. I think it's faster to do this. The first number in each row is, well, if you want the 50 15th row, the first number is 15C15. And then it comes down from there. So what's 10C7? 120. Now, Jake already told me the power on X is gonna be 7. He did exactly what we just did. He said, I know in the first term, it's gonna be 10. And then 9, and then 8, and then 7, right? So that's a 7. And if that's a 7, this is gonna be a 3. Your answer is 120 x to the 7th y cubed. Easy. Yep.
How did you know to use second?
Huh?
How did you know to use second?
I counted down. The first one's 10, 9, 8, 7. The fourth term is the one I'm looking for. Problem satisfied the fourth term. It's gonna be 10 in the first term, 9, 8, 7. Yeah, it helps when you read the problem. Okay. One more of those. Here we go. Which term do I want? This is my expansion. I want the third term. The third term. So I need a coefficient. I need a 2x and a negative y. Those are my variables, not plain x and y this time. It's 2x and negative y. Now, I wrote out Pascal's triangles in the 6th row, so getting the 7th would be easy. I don't have it up here anymore. So I'm gonna remember that the first term in the 7th row is 7C7. And then 7C6 and 7C5. So the third coefficient is gonna be 7C5. The exponent on my x, 7, 6, 5. And then my y will have to be 2 because I'm expanding to the 7. Now I'm gonna multiply. What's, is that 21? And this is going to be 32 x to the 5th. And this is gonna be y squared. All multiply, so 21 times 32, 672. X to the 5th y squared. Is that what you got?
Yes.
Perfect.
How's that bigger than the first, like the one before that?
How's, what now?
How's it so much bigger than the one before that?
Because it's got this right here.
Oh yeah. You're right.
Okay, now we're gonna start putting some pieces together. We're gonna use this same concept to do a little probability. We're gonna roll a die 5 times. And we're gonna get exactly 1, 3. We wanna know what's the probability of that happening. Now, you know what dice look like, right? So that little cube thing with the dots on it? Well, 2 of them are called dice, one of them's called a die. Okay, so I've got one of those. And I'm gonna roll it. What's the probability that I will get a 3? 1/6. So the probability of 3 is 1/6. What's the probability of not 3? 5/6. Everybody clear on that? Okay, so here's what's happening. I am gonna roll that thing 5 times. And I want one of them to be a 3. Now, does it matter to me which one it is? Like the first roll or the third roll? I don't care which one it is. So in other words, I have to have one of them be a 3, but the order doesn't matter. So I am gonna start with 5C1. Now, the 5 is the number of rolls that I have. And the 1 is the one special number I want, which I want a 3. I want 1 3. If I wanted 2 3s, this would be 5C2. Now, this problem obviously doesn't have X's and Y's like our last ones had, but it has 2 parts. It has the probability of what I want, that's like X, and it has the probability of what I don't want, and that is Y. How many, this is 3, this is not 3. How many 3s do I want in this particular problem? 1. How many not 3s do I want in this problem? 4. I gotta roll it 5 times, right? That, friends, is the answer to the question. That's how you find the probability of rolling exactly 1 3.
Can we just type that whole thing?
Type the whole thing into the calculator. Now, if you have a newer calculator that has the fraction, you know, there's the box over the box, that'll work. I gotta put parentheses. So 1 divided by 6 times parentheses 5 divided by 6 raised to the 4th power. Now, it's a probability question, so you're going to get a decimal. Expect the decimal. Want a decimal. I got 0.4019. Anybody else get that? Okay, we're gonna do one more and then I'll shut up. We've processed a lot today. I'll do one more problem. All right? So same scenario. Rolling a die 5 times. This time, I want no 2s. Okay? So when you roll that die, you could get a 2, or you could not get a 2. Right, called binomial probability. 2 things are gonna happen. You're gonna get a 2 or not get a 2. Now, I'm still rolling 5 times. This time, I want no 2s. So of my 5 rolls, 0 of them are going to be 2s. The probabilities are 1/6 and 5/6. And what are my exponents gonna be? 0 and 5. Because this is the probability of a 2, and I don't want any. This is the probability of not a 2, and I want 5 of those. Oh my gosh, you get the same thing? That's pretty crazy. Anybody want to explain that maybe by looking at well, I'm going to have, in my denominator, I'm going to have, both of them are going to have 5 6s. And in my numerator, this has 4 5s and another 5. This is 5. This one has a 1 here, but it has 5 5s here, so yeah, the fractions are the same. Coincidental, doesn't always work that way. Not every answer to every problem is 0.40.
Can I leave this here?
You can do whatever you want.
And right, just get it tomorrow.
Yep.